assuming that we had a smooth flow. And some people ask me the question after the talk, how can I consider a flow 1 over h where the initial condition has h equal to 0? Right? So I sort of have to justify that. I want to spend the first 20 minutes or so trying to justify and say what the flow really is. So the flow has a weak formulation. We'll talk about the weak inverse unconverted flow. So I'm not going to spend too much time in that. I'll just give an idea of what the flow is, and then I'll move on to give another application of the same flow, which is the calculation of the Yamabe invariant of AP3. So the idea is that you want to consider a family of surfaces NT, which solves the inverse mean curvature flow minus 1 over h mu. This is the classical equation in a weak sense. So what Huisken and Ullmann did, sort of inspired by similar constructions in the case of the mean curvature flow, they tried to they developed a level set formulation, level set in sets, which consists basically in trying to look for NT as a level set of a function u. Okay, that's sort of the spirit of the idea. I want to find a function u such that its level sets give me my family of surfaces. If you think a little bit about that, suppose you have a surface NT, and then let's think a little bit as physicists, and then the surface at t times t plus delta t. This is the variation in space. So you see that the velocity vector, right, which is supposed to be the inverse of the mean curvature, will be delta s divided by delta t. But t is just u, right? So you can write these as 1 over delta u over delta s. And this is exactly 1 over the gradient of u, right? So this is just heuristics, of course. The equation that you want to look at then is mean curvature equal to the norm of gradient of u. So the mean curvature can be computed actually as a divergence over m of the unit vector gradient of u divided by norm of gradient of u. This is the divergence in the ambient manifold. You can see that the derivative in the normal direction will vanish. So we're really just differentiating along the tangent directions. This equals to the norm of gradient of u. So that's the equation, let's see. 2 stars. So you want to find a function u which solves this equation, and I still have to say what it means to be a weak solution of that equation. Right? So this is a degenerate elliptic equation because, of course, the gradient of u could be 0 here. So it's not easy to solve such equations. An observation is that if u is a solution to that equation, then you can see u as a critical point of a functional. The idea is that you want to freeze gradient of the right-hand side. So you look at the right-hand side as given, and then you observe that if u is a solution, u is a critical point of the functional, which depends on u, and sends v into the integral of gradient of v plus v times gradient of u. Okay? Over whatever the domain is. So if you think of u as given, and you compute the Euler-Lagrange equation for this functional in terms of v, you get that the divergence of gradient of v divided by the norm equals gradient of u. So it's a kind of funny variational problem because the functional depends on the solution itself, right? But nevertheless, it's an important observation. And I'm going to assume that somehow here I have a set, which is my E naught, bounded by a surface, right? By bounded of E naught. And my initial condition will be, so the initial condition will be that the given set will be the set of points where U is negative. So I want to construct a function U, which is negative on this set, 0 at the boundary, right? And then such that the level sets of it are solutions to the inverse curvature flow. So how can we do that? Well, this is sort of similar to what happened in the Amavi problem. You can't really solve an equation, so what you can do is that you can find a family of approximate equations that you can solve. That's in general called regularization. So for this problem, it's the same thing. You have to find an elliptic regularization. So you want to approximate this equation by equations that you can actually solve, and then I'm going to refer to this as 2 star epsilon as the following problem. The equation will be divergence. Basically you do the obvious thing. This is going to be the divergence of M of gradient of U epsilon divided by square root of gradient of U epsilon square plus epsilon square minus or equal, if you want, the square root of gradient of U epsilon square. Let me put a minus here. As epsilon square equals 0. Right? So that's the equation that you want to solve for each positive epsilon. And then we're gonna choose boundary conditions. So remember that the manifold is asymptotically flat. So you have a coordinate system at infinity. So what you do is that you choose a function v to be c times log of norm of x, where c is some constantly appropriately chosen, and then you define fl to be the set of points where the function v is less than l. So the idea is that I want this equation to be satisfied in fl minus E naught. E naught is my initial condition, so that's this kind of annulus, right, in between the two regions. And I will set dirationally boundary conditions. U epsilon is going to be L minus 2. That's how Huisken and Newman do it. So you set U epsilon to be L minus 2 on the boundary of FL, and U epsilon to be 0 on the boundary of E naught. Okay? This is at least it's an elliptic equation, and actually has a geometric interpretation, which is kind of interesting. So what's the geometric interpretation? So this is kind of interesting. So you want to solve the inverse mean curvature flow in your original manifold as a level set flow. The idea is that if you go to one dimension higher, so in other words, if you look at the manifold M cross R, and if you look at the graphs of, for each positive epsilon, you look at the graph of this guy in M cross R, and then if you just translate this graph, the observation is that this translated solution will be a classical solution of the inverse mean curvature flow in M cross R. So let me write that. So if I define n epsilon t as being the graph of my function, the graph of U epsilon of x minus t divided by epsilon, right? So for each t, epsilon is fixed. I look at the graph and then I just translate. So the observation is that these guys are, they form a family. So they solve the inverse mean curvature flow. In other words, the original equation star in M cross R with a product metric. Right. And that's not difficult to check. You can, for example, you can define capital U epsilon as the function that takes x, s, and sends into u epsilon of x minus epsilon s, for example. This is a function defined in the product, right? And then you can, it's easy to see that this graph is exactly the set of points where this function is equal to t. So these graphs are just the level sets of the function capital U of epsilon. Then it's just a matter of realizing that this equation is exactly the equation divergence on M cross R of gradient of U epsilon divided by the norm equals gradient of U epsilon. Right. So that's how the epsilon square comes in. When you compute the gradient of capital U, you get an epsilon in the t direction. Right? When you compute the norm square, you get plus epsilon square over here. So we have this equation which has this geometric interpretation. So these things look like graphs. And then the idea is that the equation, one can solve the family of equations. Here involves a lot of estimates and the continuity method. Right? This is a very standard method for constructing graphs for prescribing curvature equations. You want to solve for U epsilon with these boundary conditions. The idea is that you find a one-parameter family of problems for which you can prove that the set of problems for which there is a solution is open and closed. And so open usually requires the application of the implicit function theorem, and for proving closedness one needs to prove estimates. So there's a lot of involved estimates in doing that. But you can find solutions to that equation, and these solutions will converge when epsilon, if you choose a subsequence, right? This guy is going, this family of functions is going to converge to a function U locally uniformly. Locally uniformly with gradient bounds. Again, this follows from the estimates. You prove a gradient bound, then you can extract convergence subsequences by the Arzelà-Escalé principle. So you find U by this process. Geometrically, if you look at this interpretation, what's going on? One has, so suppose that this is going to be my manifold. You have the boundary of E naught here. Here's the boundary of FL. Then I have the solution which is 0 here, and L minus 2 over here. Then I sort of I translate this guy, right? Translate this guy. So this again is a one-parameter family of surfaces which solve the inverse mean curvature flow in the classical sense. And these graphs are sort of converging to U. You have to let L go to infinity in doing that. So they're sort of converged to U. But when you make epsilon go to 0, remember that I'm dividing by epsilon here. Right? So if you fix one of these guys, let's say this, for example, and epsilon t, right? This graph over here, he's going to intersect the manifold M at a point where the function U epsilon of x is equal to t, right? This is the height 0 in the product. So when you make epsilon go to 0, what's going on is that this is sort of like pretty much fixed, but the slope is going to go to plus infinity, right? Because you're dividing by a very small number. So the idea is that in the limit, these graphs, all these graphs are going to converge to cylinders over the manifold, and the intersection of the cylinder with the base manifold gives me exactly the level set that I want. So the inverse mean curvature flow, in the weak sense, is gotten by taking these intersections with cylinders. Eventually, you can have whole regions where the function is constant. The level set doesn't really need to be a surface. It could have some interior, for example, and we can see an example of that. Okay, so these guys will converge as epsilon goes to 0 to cylinders. So the function u that you obtain by doing this has the following properties. So what are the properties of the flow? Let's see. So first of all, the function u will be proper in local ellipses. Okay, proper means that it goes to plus infinity at infinity. But the nice thing is that, remember that this equation, if you freeze the right-hand side, this equation can be seen as the Euler-Lagrange equation of this function, right? And if you think a little bit about minimal surfaces, you know that if you have a minimal surface in M cross R, which is a graph, it's not only a solution of the equation mean curvature equals 0, but it's also minimizing. There's a calibration argument that you can do, improve the graphs, always minimize area in the homology class. So if you take this idea to this setting, you can sort of consider, you can choose essentially gradient of u divided by gradient of u by norm of gradient of u as the vector of the calibration. If you take this idea to this setting, you get a minimization property. Wait a minute, here. Minimization property. Well, what you have to do is first to deduce the minimization property at the epsilon level and take the limit as epsilon goes to 0. So the minimization property is that u is not only a critical point of this function, but it's actually a minimum point. So ju of u will be less than or equal to ju of v for any v such that the set of points so that two functions are different is compactly contained in m minus e naught. So there is a minimization principle that is satisfied by u, and again, I won't have time to discuss that in detail. But when you translate this to the level sets, you get that you conclude that the level sets of the flow actually minimize area with respect to all surfaces on the outside. That's a property. Let me give a definition. This is sort of a summary of the properties of the flow. So you say that E open set is a minimizing whole. Right. If it minimizes area on the outside. In other words, let's say in some domain omega, if the area of the boundary of E intersected with any compact set, intersected with omega, is less than or equal to the boundary of F intersected with omega, for any F containing E, and such that the difference is compactly contained in omega. So let me draw a picture. Maybe I should erase this. So the picture would be something like this. You have this set. This is a general definition. You have a set omega, some guy E over here. So then you want to compare E to all the set F which contains E. The difference compactly contained in omega. It's a minimizing whole if the area of the boundary of F is always bigger, greater than or equal to the area of E. So think of a convex sphere, for example, in Euclidean space, right? It always minimizes area from the outside, and you say that E is a strictly minimizing whole. If equality in there implies that the sets are the same. Well, the sets are the same almost everywhere. I can actually, to be precise, one can work with general sets with finite perimeter, and this would be the reduced boundary. But let me not discuss this property. So these are general definitions. Let me just give one other general definition. Suppose that you have a C1 surface N inside a manifold M. Right? You say that H, suppose that you have a function H on N which is locally integrable. You say that this is the weak mean curvature. Weak mean curvature of N if the first variation formula holds for H. So the equation is, if you look at the first variation formula of area, you see that the classical formula gives you the divergence of a vector field over sig over n, right? Integrated on n. And this is supposed to be equal to minus the integral of the vector field and the mean curvature vector. If this formula holds for any smooth vector field with compact support, you say that the x is the weak mean curvature of the surface. That's a definition. So mean curvature can make sense for some C1 surfaces, and actually all of these level sets will have a weak mean curvature in that sense. Okay, so let me just finish with the basic properties of this flow in terms of these minimization definitions, so that we have some intuition and maybe explain why you can work with minimal surfaces as initial conditions. So some properties will follow. First of all, ET is always a minimizing whole. For any positive t. This is something that you can prove using the minimization principle. Not for t equal to 0, because you could have started with an arbitrary open set. Maybe not a minimizing whole. But for for any positive time, this property is actually true. So that's the first property. Right, let me just fix some notation. ET is the set of points where u is less than t. Okay? The sub-level sets. And NT is actually will be the boundary of the set of points where u is less than t. So you can actually prove that NT for any t is a family. So they are C1 alpha surfaces. So the regularity theory doesn't give you C2, but they are C1 alpha surfaces with a weak mean curvature. With weak mean curvature. Well, the mean curvature here is just given by the norm of the gradient of u, right? That's what we expected. Okay. Right, this is almost everywhere. But this flow can actually be discontinuous. So let me draw a picture so that we can understand what I'm going to say. I sort of mentioned this example in the previous talk. If we start with two round spheres, let's say they're very small. Suppose that these two round spheres are give you the initial condition. So initially they will flow by classical inverse mean curvature flow. So you have two balls as the sub-level sets. So at some point, your sub-level set will be made of two spheres. So here u is less than, let me amplify this picture. So u is less than t here, and u is less than t here. But at some point, you'll reach a configuration such that the set ET is still a minimizing whole, but it's not strictly minimizing anymore. Strictly minimizing means that if you have equality, then the domains have to be equal. But at some point, you'll see that if you remove two small balls here and add a catenoid, minimal surface here, you realize that the domain that you get in this way has the same area. So this means that ET is not a strictly minimizing whole anymore. So when that happens, actually the flow will fill this region. I hope you can see what I'm going to write. This is going to be a region where u is constant equal to t, and then outside u is bigger than t. So there's a jump. At some point, you have two spheres jump into a single sphere after time t. So that's the picture that we have to have in mind when I write the following things. So the idea is that this family of surfaces is continuous from the left. So ns converges to nt as s increases to t. Right? But it might not be continuous from the right. So you see that you can prove that ns converges to the following set. The boundary, think of the picture of the interior of the set of points where u is less than or equal to t, as s converges to t from the right. So that's what's happening there. Right? Let me call this set by ET plus. Right? So this is the set ET plus, and you can actually prove that ET plus has the following property: is the smallest strictly minimizing whole. It is a strictly minimizing whole, and it is the smallest strictly minimizing whole that contains ET. And this property holds even for t equal to 0. So you start with a set which may be arbitrary, right? No special property, but when you look at the convergence as t goes to 0 from the right, looking at positive t, this is saying that the surfaces might not converge to the original boundary, but they will converge to the boundary of the smallest strictly minimizing whole. So if I draw a picture, let's see here. I can have a situation like this, right? I can have like maybe a small minimal surface here, and then it goes like this. Sorry. So you have a picture like this. So you can choose your E0 like that. Like this minimal surface. But what's going to happen is that here, the smallest strictly minimizing hole that contains E0 is here. Right? So this is the E0 plus. So the surface the flow will automatically fill all this region with U equals 0, and we will start from that. So that's why for the application, one needs to impose that the boundary is such that there's no minimal surfaces on the outside. Because you want the property that the flow, when t goes to 0, the flow has to converge to the surface itself and not to the minimizing hole over here. Right. Okay. And in the proof of let me just say that in the proof of the Riemannian-Penrose inequality, the key issues are, well, first you have to construct the flow, right? But then we want to apply the monotonicity of the Hawking mass. So one has to make sure that the Euler characteristic, let me put it this way, you have to make sure that NT stays connected, right? Because it's when we applied the monotonicity, remember that there was a term which we needed the Euler characteristic to be less than or equal to 2. And one has to prove that the ADM mass is greater than or equal to the limit as t goes to infinity of the Hawking masses of NT. Here there's a little issue because one would expect that you have equality here. So the surfaces should converge to round spheres. So the Hawking mass should converge to the mass. But there's a technical problem that one can only get C1 alpha close. So it's not so far possible to prove equality, but you can argue that it's greater than or equal to. Right. No. The scalar curvature needs to be, certainly needs to be connected here, right? But this is pretty general. This works for any asymptotically flat manifold. No, you need hypothesis, no hypothesis on the curvature, but you need the infinity to be well behaved. So it works for any asymptotically flat manifold. Actually, there's a more general theorem. You need to find a subsolution, which is sort of related to the behavior at infinity. But it might work in other settings as well. Yeah, it still holds. Right. The curvature is not relevant for this discussion. Curvature will be important to get the monotonicity of the Hawking mass, right? But not for the weak formulation of inverse curvature flow. Right. Okay, this is what I wanted to say about the flow. Any questions about that? If not, we will move on and talk about another application. Okay. So does that solve the problem of dividing by 0, Howard? No? Hmm? No, the idea is that you produce a solution by the regularization procedure. Right? So there's no you forget about 1 over h. You look at the I erased the equation. No, u is proper. U is going to go to plus infinity at infinity. Right. No, because as I said, you remember that my u epsilons go to L, right? The regularization procedure. You have to control the u epsilons, but you know this is a kind of barrier argument, and you can prove that in the end u is proper. You cannot be constant. Maybe you can be constant in a compact manifold or something like this, but not in an asymptotically flat. What? No, in this setting cannot be constant. Okay, my hypothesis is that at infinity it's asymptotically flat, right? Yeah. So I'm assuming that M is asymptotically flat. So U has to go to plus infinity at infinity. Okay. Right. So so now let me talk about the second part, which is the Yamabe calculation of the Yamabe invariant of RP3, using again the inverse curvature flow. So let me give some motivation, which Zindine, I guess, already talked about. Let me just recall some formulas. So what we want to consider a three-dimensional manifold with a metric G, let's say compact. Then one defines the energy of G as the integral of the scalar curvature of G over M divided by the volume. In this case, since we are in dimension 3, is the volume to the power 1/3. This is the Einstein-Hilbert functional. So that's the function that plays a key role in what I'm going to talk about. Okay, and the remark is that G is a critical point of E if and only if G is Einstein. This holds in general for any dimension if you put the right power here. And in dimension 3, actually, one knows that Einstein metrics are the same as constant curvature metrics. So these metrics are the critical points of these natural functions. So we're sort of interested in the values that this functional can assume. So an example, the basic example is given by the round sphere, right, S3 G naught. Let's say G naught has constant curvature 1, for example. Then one can compute that the scalar curvature will be 6 and that the volume, if I remember correctly, is 2 pi square. So when one computes the energy of G naught, one gets the integral of 6, right? Then we get a volume term in the numerator, a volume term in the denominator. You get 2 pi square over 2/3. So that's the constant for the round sphere, and this is going to be my definition of sigma 1. Sigma 1 will be this value, the energy of the round sphere. Right. So I guess Well, Zindin already talked about this. Let me just recall that the Yamabe constant, y of G, of a metric G, is just the infimum. Maybe the notation will be a little bit differently, but the notions are the same. Is the infimum of all the energies, right? For all metrics which are conformally related to G. So G bar is going to be u of x to the power 4. In this case, the correct power is 4, u positive. Right? That's the Yamabe constant. And the relevance is that if you want to find critical points of this functional, you see that the functional is bounded. First of all, it's not bounded from below or nor from above in general. So any critical point would have to be a saddle point. But in conformal classes, it is bounded from below. So you can first minimize the invariant, which amounts to the Yamabe problem. And then you can take the sup over all conformal classes. So this is the Yamabe constant. Let me put the conformal, right? It's not topological, but it depends only on the conformal class of G. Okay, right? And then there is a result of Obata, which also appeared, I guess, more or less, which is sort of related to the, yeah. There's a result of Obata which says the following, that if G is Einstein, then the infimum, in other words, if G is Einstein, then G realizes this infimum. The conformal constant will be exactly the energy of G. So any Einstein metric is the minimizer for the Yamabe energy, and actually one can prove that it is the unique constant scalar curvature metric inside the conformal class. So one knows, for example, that since this metric is Einstein, right, the round metric on S3, one knows from this result that the constant, the energy coincides with the conformal Yamabe invariant of G naught. Okay, and I saw that Zindin talked about this today. One can prove the following proposition: that the Yamabe invariant, Yamabe constant of any given metric is always less than or equal to the constant of the sphere. You can always, this is an infimum, right? It's defined as the infimum. One can always construct a test function, a family of test functions, such that the energies converge to sigma 1 in some sense. Geometrically, I saw that he did the calculations, but let me just make a picture here. One would have a manifold, maybe with some topology. What you do is that you choose a point, small ball, and sort of construct a function which basically shrinks the complement of the ball to almost a point. The topology is over here. And then in this little ball, after you do the conformal deformation, what you see is an almost round sphere, right? So that's this is a family of, so you have, this is G, this is U epsilon for G, right? And then as epsilon goes to 0, the energies of these guys will converge to the energy of the round sphere. Okay, this is saying then that all the conformal, the Yamabe constants are all bounded from above by sigma 1, then it's natural to take the sup. So the Yamabe, let's see. Let me call it sigma to sigma invariant, which was considered by Rick Shen and also Kobayashi. What you do is that you define the sigma of M to be the sup of all the Yamabe constants. over all Riemannian metrics in M. Since they are all bounded from above by sigma 1, this is always bounded above by sigma 1. And the problem is compute that. Right? Compute that for given topologies. So this now is a topological invariant. And actually, let me say that the actual value of the constant is not that important. What is more important is that you see the geometry, right? What's happening? What's happening when you take the supremum of these constants geometrically, and of course from that you get the actual constant. So just some examples. We are very far from knowing the invariance of three manifolds. Some known examples. The invariant of a 3 torus is equal to 0. First of all, the 3 torus admits a flat metric. Right? And a flat metric is, of course, Einstein. So the conformal invariant of the flat metric coincides with the energy of the flat metric, but the energy will be 0, right? Because the scalar curvature is 0 in that case. So you can always find a conformal class such that this is 0. So this already tells me that the invariant being the supremum has to be non-negative. But you can see this. Let me just do a remark that the invariant being positive is equivalent to the fact that M admits a metric with positive scalar curvature. And we know from Shen and Yao, and also Gromov and Lawson, that the 3 torus does not admit any metric with positive scalar curvature. So the invariant cannot be positive, but it is non-negative, so it has to be 0. That's the argument for the 3 torus. The other example that is known is S2 cross S1. This guy, you actually get the constant sigma 1 for the sphere. What's the explanation? Well, first of all, it has to be less than or equal to sigma 1, right? But what you can do is that if you take you think of S2 cross S1 as a very long cylinder, the conformal class will depend on how long is the circle factor, right? With these two sets identified. So the observation is that as you make the length go into infinity, one can find a conformal deformation of that, which geometrically looks something like this. This is part of a Delaunay, sort of like a Delaunay family. I'm just going to draw a piece. With these two guys identified. Right? And this will be almost a round sphere. Right? It's the same fact that if you're used to Delaunay surfaces, right? As you make the next size go to 0, the surface converges to a chain of round spheres. So this gives me a family of conformal classes such that the invariants actually go to sigma 1. So the constant is sigma 1, but it's never achieved. Right? There is no. It's part of the solution of the Yamabe problem that you can. The only conformal class that achieves sigma 1 is the conformal class of the round sphere, but it can get arbitrarily close. So the sup is sigma 1 anyway. Okay. So what I'm going to talk about is there's a conjecture due to Rick Shen. Well, the conjecture is that metrics of constant curvature should realize the Yamabe invariant, Yamabe sigma invariant. In particular, as a corollary, this is a conjecture of Rick Shen that if the manifold is obtained from the 3-sphere by a quotient of a group of isometries, and suppose that the group of isometries, let's say, has n elements, right? Then the IMAB invariant of n should be sigma 1 divided by n to the 2/3, I guess. N to the 2/3. Right. That's the conjecture. And that's the natural thing, that this is exactly the energy of the constant curvature metric. Constant curvature metric on n. And this is going to be my definition of sigma n. Right? So in other words, the conjecture says that the round matrix in the spherical setting should realize the topological invariant, IMAB invariant. Should realize the soup. That's the conjecture, and the theorem is that that I want to talk about. This is due to Bray and Neves, 2004, is that the invariant of AP3 is sigma 2. So they proved the conjecture for the case of the projective space. AP3 is the S3 quotient by the action of the antipodal map. And this is an application of the inverse curvature flow. Okay, so I want to talk about the proof of this. First of all, what is easy to see is that it's easy to see that the invariant is a supremum, right? And of course, among all metrics, you have the constant curvature metric there. So, which is Einstein, and therefore realizes the conformal constant. So the remark is that the invariant of AP3 has to be greater than or equal to sigma 2. Right? The same here. You always have greater than or equal. The problem is to show that it's less than or equal than. So the strategy is prove that the conformal IMAB constant is always less than or equal to sigma 2 for any metric G on AP3. So you have to pick an arbitrary metric on the projective space and prove that the Einstein-Hilbert, that the conformal IMAB constant is at most sigma 2. Right? So if you prove that, of course, taking the supremum, we get the other inequality. So how do we do this? Okay, first of all, of course, we can suppose that the invariant is positive, right? Because otherwise it's trivial if it's negative. And it's quite surprising that there is a connection of this problem with the theory of asymptotically flat manifolds and with the monotonicity of the Hawking mass. So what's the connection? You suppose that the invariant is positive, then it is known, the solution of the IMAB problem, implies that there exists metric G naught, right, conformal to G with constant scalar curvature. Constant scalar curvature. Let's say R naught and positive because the sign of the constant has to coincide with the sign of the conformal invariant. So you can always talk about this G naught. Now you recall the definition of the conformal Laplacian. Remember that my Laplacian is minus the Laplacian that's been used in the other talk. But anyway, the conformal Laplacian will be, in dimension 3, will be this. Right? Conformal Laplacian. And remember that the conformal Laplacian is the operator that tells you how the scalar curvature changes under conformal deformations. And now because this constant is positive, now we have a negative sign of this guy, and then we can construct a Green's function, a positive Green's function for this. So we write this. So because the constant is positive, one can prove that there exists a Green's function G, right? Given a point P, I would choose a point of L naught at P. And this means that one can find, let's say, a positive Green's function. One can find a function which satisfies the equation L naught of G is equal to 0 outside the point P, and such that the function goes to plus infinity at P. So one can normalize it such that as you take the limit of G of Q times the distance of Q to P, as Q goes to P, this is 1. This is just a choice of normalization. So, okay, there's always this Green's function. So what does this mean? What is the geometric interpretation of that? So now what to do is that you define another metric, which I'll call GAF, because this is going to be asymptotically flat. This is going to be the conformal deformation of G naught, right, by the Green's function. Since the Green's function is positive, right, this is a metric that makes sense outside the point P. And one can check that the scalar curvature of this metric from the formula, right? If I remember correctly, you get a minus 8 G to the minus 5 L naught of G. This is the formula for the scalar curvature. But since G is a solution of the equation, we get 0 here. So this is an asymptotically flat, and also a scalar flat manifold. The idea is that you're sending the point P to infinity. Right? So let me just draw a picture. If you do this to the round sphere, you get the Euclidean space through stereographic projection. So this is a sort of generalized stereographic projection in some sense. So we start with a manifold, right? Pick a point P. This is supposed to be AP3, right? And then you blow up the point P to infinity. You get this asymptotically flat guy. And here you get an AP3. So this is GAF. This is the meaning, the geometric meaning of the construction. So now we have 3 metrics, right? We have the original metric G, which we wanted to compute the Yamabe constant. We have the metric G naught, which is the solution to the Yamabe problem, and we have the metric GAF. What do they have in common? Well, they're all conformal to each other. They're all conformal to each other. Of course, in the case of GAF, I have to take out the point P. But they're all conformal. And the Yamabe constant is a conformal invariant. So now the idea is that instead of computing the Yamabe constant of G, I'm going to translate the energy functional into the energy function of GAF and see that the infimum is basically the same because they're all in the conformal class. So let me just write this. Okay. Actually, this connection with asymptotically flat manifolds was important for the solution to the Yamabe problem, right? Because in the remaining cases, because there's a connection with the positive mass theorem. So this is not new. Anyway, the invariant of G is going to be equal to the invariant of G naught, and this is equal to the invariant of GAF, and this is going to be equal to the following thing. The Yamabe constant is an infimum, right, of the energy. Remember that, let me just write, I think I didn't write here, right? So so let me just write the formula here. One had a metric G, if one considers G bar to be U to the 4G, the energy of G bar will be equal to, because of the constants here, will be equal to 8 times, let's see, how does this work? Integral of 8 times the gradient of U square plus U square divided by U to the 6 1/3. Right? This is the formula for the energy of a conformal metric in this particular case. Right. So if, sorry, okay, there's a scalar curvature term. And maybe this, is this correct? I'm confused with the constants. Yeah, I think it's correct. So now, if you look at this expression with respect to the asymptotically flat metric, the GAF, you see that the scalar curvature term is 0, right? We already computed that. So what one gets is the following term, gradient of U square GAF divided by integral of U6 1/3. And here, let me just say that U here will be the Sobolev space of M minus a point with compact support, for example. It's not difficult to see that when you define the Yamabe constant, you can remove a very small ball, and the constant will be the same, right? If you consider functions which vanish in neighborhoods of a point, you won't affect the constant. So now we have this interpretation, but this is just the Sobolev constant, right? Zindin wrote in the end the Sobolev inequality for Rn, but you can talk about the Sobolev inequality for this asymptotically flat metric as well. The only difference is that it comes with an 8 here. But then the observation is that this is exactly 8 times S of GAF, where S is the Sobolev constant. Oh, maybe the inverse of the Sobolev constant or anything, but let me just put it this way. So now the idea is we have a connection between the Yamabe constant and Sobolev constants of asymptotically flat manifolds. So now, instead of proving this, what we're going to prove is the following. And this is actually a theorem. Given any, let's see, asymptotically flat metric on RP3 minus a point, suppose that, I guess I need to assume that the scalar curvature is non-negative, then the Sobolev constant of G will be at most sigma 2 divided by 8. Right. So when you multiply by 8, you get the result. So the idea is now we forget about the compact manifold, at least for a while, and try to estimate Sobolev constants of asymptotically flat manifolds. So how do we do this? Okay. So I have a little bit more than 10 minutes left. So let me talk about the model case, and then in the next talk I will finish the proof. So what's the model case? The idea is that if you want to estimate a Sobolev constant from above, what you have to do is you have to produce a test function. It's like the Yamabe problem. You need to produce a function and estimate that. And in general, when you want to, for the test function constructions, one usually needs to understand first the model case. If you understand the model case, you have natural functions for the model that then you try to transplant to the general setting. So let me talk about the model case. So the model case is just RP3 G naught with a metric of constant curvature. Constant curvature. What? And the surprising thing is that when you look at the model, the Schwarzschild manifold is going to appear. Let's see why. So this is the model. I'm going to look at the universal cover, which is just S3. I will denote the metric by G naught again, right? So I want to remove a point in the projective space. When I look at the cover, this is equivalent to removing two antipodal points, which I'll suppose that they are the north and the south pole. Right? So I have the two poles which are removed, and I have my sphere of constant curvature. Now, remember that in RP3 G naught we have a Green's function G, which we can lift to the sphere, right? So we consider G to be the lift of the Green's function. And now this function G on the cover will be a solution of the equation in the complement of the two poles, and we'll go to plus infinity at each of the two poles. G now goes to plus infinity here and goes to plus infinity there. So now you look at, you do a conformal deformation, right, by G for naught. And then it's easy to see that what are the properties of this guy. First of all, it will be asymptotically flat, because G goes to plus infinity with the right asymptotics. Now this guy is going to have two ends, right, which correspond to these two poles. And it's not difficult to see that this guy is going to will preserve the symmetries. The sphere is rotationally symmetric. Right? So the Green's function will also be rotationally symmetric, and the resulting manifold then will have a rotational symmetry. Then it has to be a Schwarzschild. In the previous talk, I did some calculations which ended up with the Schwarzschild. And the same way you can argue here. The only rotationally symmetric manifold of zero scalar curvature, also has zero scalar curvature, is the Schwarzschild. So the picture would be something like this. Okay, the Schwarzschild. Well, there's a one-parameter family of Schwarzschilds according to the mass, but they are all scalars of each other. So one of the Schwarzschilds will be. Okay, so what's the conclusion? Well, the conclusion is that suppose that I take half Schwarzschild, right? Let me draw it here. let's say that I choose the Schwarzschild to be 1 plus 1 over norm of x times delta. So if you want the mass here, would be 2, right? So in this way, the minimal surface will be the boundary of the ball of radius 1 in this coordinates. So I'm going to denote by LS. This is the definition. Will be this manifold, right? R3 minus the ball with this metric. Well, let me say after antipodal points on the boundary are identified. So I look at the half Schwarzschild, and then I identify antipodal points on the boundary. So when I do this, I have no boundary anymore, because I will have a projective plane inside and then just one end. The topology will be exactly RP3 minus a point. Right? Topology. RP3 minus a point. This is going to be my manifold LS. And what this is saying, right, that when you look at the curve, do the conformal deformation and look at this, is that if you do the same, if we go back to the original setting, right, what we concluded is that RP3 with the metric GAF, remember the GAF is the stereographic projection, is going to be a scaling of this manifold LS. We know that this is a Schwarzschild. Maybe we don't know the mass. One could compute, but let's not worry about that. It has to be a multiple of this metric here. Right. Okay, so if we look at RP3 with the constant curvature metric, pick a point P, send the point P to infinity by this construction, what we get is half Schwarzschild with antipodal points on the boundary identified, up to a scaling. That's the conclusion. Okay, so I have 5 minutes left. Let me see what we do now. So now the idea right. So now I know my manifold, right? Now the idea is that I can see my original guy as a conformal deformation of the asymptotically flat guy. So let me write, I can write G naught, which is the constant curvature metric, as a function U naught of x to the power 4 times GF. I'm reverting the process. Instead of blowing up, I'm blowing down. And the conformal factor is U naught of x. So now the point is that this is a function on the asymptotically flat manifold, so I can look at this quantity, right? the Sobolev ratio. But remember that this constant is exactly the energy of the metric that you get when you do the conformal deformation, right? So the Sobolev ratio of this guy is going to be the energy of G naught. But the energy of G naught is the Yamabe constant of G naught, which is just sigma 2. Right? We already computed that. So the conclusion is that U naught achieves the infimum in the Sobolev inequality. In other words, if I look at the ratio, integral of gradient U naught square in the asymptotically flat guy divided by 6 to the 1/3. This is going to be exactly sigma 2 over 8. The 8 is just because the 8 appears in the formula, right? So U naught is really achieves the infimum of the Sobolev constant. And let me say that now the observation is that we have symmetries. So since everything here is rotationally symmetric, the function U naught will also be rotationally symmetric. So actually it will be a function only of the level sets. So U naught is rotationally symmetric. I'm talking about the model case here, right? It's rotationally symmetric. So now let me just finish with the inverse curvature flow. So what's the inverse curvature flow? You take sigma of 0 to be this minimal surface here after we identify the antipodal points. Right? This is going to be the boundary. After we identify the antipodal points. And then it's easy to see because it's just the model case, right? That we can define sigma t here. And we can choose the parametrization so that this sigma t's actually solve the classical inverse mean curvature flow. So I'm going to denote by sigma of t the solution to the classical inverse mean curvature flow. Of course, the flow doesn't make sense at t equal to 0, but what I want is that sigma t converges to sigma of 0. So I'm just talking about this flow over here. It starts here. And because they all have constant mean curvature, right, it's easy to see that the solution will be formed of exactly the leaves of the foliation. Okay, and now the point is that the function U naught, since it is rotationally symmetric, actually is a constant on the sigma of t, right? So you define f of t to be, let's see if I get it right. Let me first say that sigma of t in the level set formulation is going to be the set of points where some function phi is equal to t, right? Where phi is also rotationally symmetric. And then you can define f of t to be the value assumed by U naught at the surface sigma of t. So this is my function f of t. Let me see if I forgot something. Right. For t non-negative, right? So this is just a definition. This is a function of t. In other words, one can write U naught as being f composed with phi, right? Because remember that at the level set, the function phi is equal to t, right? At the level set here. So what I'm just saying is that U naught, we all have symmetry here, right? Everything is rotationally symmetric. So the function that realizes the infimum of the Sobolev inequality is rotationally symmetric, is a function, is a constant in each level set. You take f of t to be this constant. And just, if you want to rephrase this, you can just see that the function U naught is going to be f composed with phi, right? Now what's the basic observation so that I can continue next time is that this is the model case, but in general I have to work with an arbitrary asymptotically flat metric, right? And I have to estimate the Sobolev constant. So again, to estimate Sobolev constants, I need to produce test functions. So the idea is you start with this asymptotically flat manifold. You pick a minimal surface, you solve the inverse mean curvature flow, you have a foliation of the sort sigma of t, which is given by the level sets of a function phi. So I have this function phi defined on my manifold. Then I just take as definition of u as being f composed with phi, where f is this exact function here. So in some sense I'm looking at the model, picking the function, transplanting it to the general situation. After one does this, one has to estimate the Sobolev ratio, and then it's interesting that in the calculation, the monotonicity of the Hawking mass again will play a role, and you get the sigma 2 over 8. So that I can do in the beginning of next talk. Are there any questions? If not, yeah.